So now let's focus our attention to oxyacids, which contain an OH bond with an X group on it. And I've listed 4 of them here: HClO4, HClO3, HClO2, and HClO. I've also drawn the structures of them out here. And let's compare the Ka, or the acid strength, of each of these acids. For HClO4 and HClO3, our Ka is very, very large, and we consider these to be strong acids. For HClO2, we have 1.1 times 10 to the minus 2 for the Ka, and for HClO, we have 3.0 times 10 to the minus 8 for the Ka. So let's try to determine some type of trend to figure out why the Ka decreases so much down this series. So acidity is directly proportional to the number of terminal oxygens and oxidation number. The larger the amount of terminal oxygens, the higher the Ka, and the larger the oxidation number, the higher the Ka. So let's look, if we look at the oxidation number of each of these chlorines in each of these acids, we have plus 7 for HClO4, we have plus 5 for HClO3, we have plus 3 for HClO2, and we have plus 1 for HClO. In addition, we want to look at the number of terminal oxygens, and a terminal oxygen is an oxygen on the very end of the structure that's not connected to a hydrogen. So HClO4 has 1, 2, 3 terminal oxygens. HClO3 is only going to have 2 of them. HClO2 only has 1, and HClO doesn't have any. So the terminal oxygens are indicated here with the red circles, and they're going to dictate how particularly strong or weak an acid is. We can go over a couple more examples. So let's look at H2SO4 versus H2SO3. And if we draw the structures of each of the 2 of these, H2SO4 is going to have an SO4 group with hydrogens here on 2 of the 4 oxygens. If we look at the oxidation state of the sulfur, it's going to be plus 6. If we would compare this to H2SO3, we would have the same parent structure here, but in this particular case, we only have 1 extra oxygen to put on here. Our sulfur oxidation state is also going to be plus 4. So here we have 1 terminal oxygen, here we have 2 terminal oxygens. Okay, so H2SO4 would be a stronger acid than H2SO3 because it has 2 terminal oxygens and a higher oxidation state than the H2SO3. Likewise, we can compare H3PO4 versus H3ASO4. If we look at these structures, both of them are going to be very, very similar. Okay, they're in the same period of the periodic table, so we have PO4 here, and we have 3 hydrogens that we have to put around this. Okay, its oxidation state is going to be plus 5, and there's going to be 1 terminal oxygen. For H3ASO4, we put 4 oxygens around here, and then we have to attach 3 hydrogens to these. Okay, the oxidation state here is also plus 5, and we have 1 terminal oxygen. So in this case right here, polarity will dictate the acid strength. And if we look at this, our H3PO4 bond is going to be more polar than our H3ASO4 bond. So H3PO4 is going to be greater than H3ASO4 due to polarity. So the more polar the bond that we have that's connected to the oxygens, the stronger our acid is going to be. So this is what we would look at when we're looking at oxyacids. And in the next video, we'll look at a specific case and deal with carboxylic acids.